In this video, we're going to be discussing acid concentration as measured on something known as the p-scale. That might seem a little mysterious, but the terms below might seem a little more familiar. We're going to be talking about how to calculate pH and pOH. Let's start with a quick list of the learning objectives in this video. We're first going to discuss the general idea of what acid concentration really means. This is something we'll reflect on again towards the end of the video when we're calculating the concentration or the pH of particular solutions. And then we're going to talk about the p-scale. Sometimes people don't realize that the p-scale is actually a mathematical scale that scientists have used for many different things, including pH and pOH. It's really just an easy and simple way to keep track of very, very tiny numbers, which is what pH and pOH is typically about. We'll talk about the p-scale in general first, then focus more our time on the idea of pH and pOH, which again are measurements of the concentration of hydronium ions in solution. Once we're done with that, there are actually a couple extra equations that you guys can use and have at your disposal to allow you to very easily convert between the two of them. If you measure the pH of something, you can very easily convert it into the pOH. Once we talk about the mathematics, we'll actually take a break before we do some problems and talk about how to measure pH. pH can be measured chemically as opposed to just calculated mathematically. We'll then talk about how to calculate the pH of a strong acid. If I have a 1 molar solution of HCl, I should be able to determine the pH of that solution, again, the concentration of HCl+. And then finally, we'll put all this stuff together and we'll practice some problems doing some of these calculations, calculating pOH, calculating acid concentration. Let's start our discussion by talking about what acid concentration is really all about. It's basically measured as the amount of H+ ions, or if you're talking about the Bronsted and Lowry model, H3O hydronium ions, their concentration in water. Just like we can measure the concentration of anything else in terms of how much there is per volume of liquid, we can measure the concentration of H+ or H3O ions. This measurement is done in the units of molarity, so it's going to be moles of H3O+. Per liter of solution. We can take a second actually just to write that down. Our molarity is going to be moles of H3O plus per liter of solution that we're dealing with. We have actually a symbol system that we use to represent the concentration of pretty much anything, but it's going to start with the molarity of a solution. And when we want to talk about molarity, we actually put the substance in brackets, and those brackets automatically mean, these brackets here, these brackets automatically mean molarity or concentration. That all being said, we can therefore keep track of the hydronium ion concentration or the hydroxide ion concentration by simply putting the symbols for these two chemicals within brackets. And again, we're talking about molarity of both of these substances because, again, that's what the bracket symbol is telling us. Before we dive into some of the mathematics, one last thing to talk about in terms of acid concentration. This acid concentration, the H3O plus concentration, is dependent on the acid it comes from. And this is something that can be a little tricky to start things off with. For example, we can start with the chemical HCl, one of our strong acids. HCl dissociates 100% to create the H3O plus ion, the hydronium ion, and the Cl minus ion when in solution. What we can say for then is for every 1 mole of this stuff we start with, we can expect to get 1 mole of H3O plus ions into our solution. Therefore, if we put 1 mole of HCl into 1 liter of water, we can do some quick mathematics and we would find out that our H3O concentration is 1 molar. The 1 mole of HCl, the 1 mole of H pluses for 1 liter, and we get a 1 molar solution. This all seems very straightforward, but I think you'll see in our next example why it's very important to point this out. Again, we're going to say that H3O concentration is dependent on the acid that it comes from. Here is yet another reaction showing the dissociation of the hydronium ion from the actual salt it comes from. And as a result, in this case, we get a little bit of a different process here. Because the base here, because the SO4 has a -2 charge, we need 2 hydrogen ions to balance it out, and as a result, when this stuff goes into solution, we get 2 H3O pluses for every 1 mole of this we start with. So we can therefore say that 1 mole of H2SO4 will put 2 moles of hydronium ions into solution. We're going to get more hydronium per molecule or per mole of molecules that we start with. As a result of that, 1 mole of H2SO4 in 1 liter of water, just like we had from before, is now going to create a 2 molar solution of hydronium ion concentration, and we're going to get twice as many. And again, it has to do with the fact that this acid has 2 hydrogens in it, whereas the HCl only had 1. We actually have a word to describe these. This was something described as a diprotic acid. Di, as we recall, meaning 2, and protic refer to the fact that it gives off 2 protons. So we would talk about this acid as being diprotic, and again, we would expect our concentration to be twice as high as we did with a monoprotic acid. As you might imagine, there are also triprotic acids. That's about as far as it tends to go. But again, this differentiation is going to be something we'll need later when we're looking at the concentration of solutions made from different types of acids. All right, well, let's get into the heart of the conversation for today, and that's measuring things on the p-scale. As we mentioned before, the p-scale is simply a convenient scale for keeping track of very small numbers, and our hydronium ion concentrations are going to be just that. They're going to be very, very tiny numbers. As opposed to writing tons of stuff in scientific notation, we can instead use this p-scale, which is simpler to work with. Now, the downside to the p-scale is it is a logarithmic scale, and I find students are very uncomfortable sometimes with this logarithm concept. The good news is you don't have to do too much with logarithms. It's really going to boil down to a formula, but there are some basic things you need to understand. Each unit in the logarithm scale, 1, a 2, and a 3, represent a factor of 10. That means for us, as we can see down here in this bullet, that the number 2 in the log scale is actually 10 times bigger than the number 1. So if you have something with a pH of 1 versus a pH of 2, that's going to mean that pH 1 is actually 10 times more concentrated in the H plus ion concentration than the thing with the pH of 2 is going to be. It's not just an increase of a factor of 1 as we would normally expect on a linear scale. And in general, no matter what you want to keep track of on the p-scale always has the same exact formula. P of n, which means this is the item we want to keep track of on the p-scale, is always going to be the negative log of whatever that value n is. So here's where we would plug in our concentration, and then we would just take the negative log of this particular concept. This is all a lot clearer and easier to understand when we actually talk about what we're dealing with here, and that's the concepts of pH versus pOH. If you want to keep track of pH, which is a way of measuring the H plus ion concentration, we're simply going to take the negative log of whatever our H3O ion concentration actually is. This is usually a number we can either given or calculate. We can plug it into this formula, and as a result, we can calculate the pH of our substance. Likewise, the concentration of OH ions in our solution is something we can measure or calculate. We can plug that number into this equation, and that'll give us the pOH of our individual solution. Again, the logarithm thing can be a little bit scary, but overall, this is not a difficult equation to work with. It's important to remember, though, that this guy is a measure of H3O plus ion concentration, or acid concentration, whereas this one is a measure of OH minus ion concentration, or otherwise base concentration. As we'll see in a moment, these two concepts are actually very, very closely related together. Before we continue and talk about some more of the mathematics we're going to be dealing with, I think it takes a minute, now that we've identified what pH is, it takes a nice minute here to kind of talk about what it is we're actually dealing with and where these acid and base ranges is. This is something you should have seen in the past, but maybe it's something that requires a little bit of reminding. First of all, we'll start in the middle, which is where neutral stuff is, and you can see over here this is defined as being neutral, and that's things that have a pH of 7. When you have a pH of 7, that means your acid concentration and your base concentration are actually equal to one another, and they pretty much cancel out. The lower we go on the scale, from 7 down to 0, that's increasing acidity, meaning things are getting higher and higher in your H3O plus concentration. And as we go further down the scale, this is increasing alkalinity. That means these guys have higher and higher OH minus concentrations. And the further we get away from this middle point of 7, the stronger and stronger each of these three individual things kind of get. If you're comfortable with your logarithm scale, we can actually see how this works mathematically as well. For example, something that has a pH of 1, you'll be able to mathematically calculate later on that this stuff has an H3O concentration that is equal to 1 times 10 to the negative first molar concentration of H3O plus. The log thing, the pH scale that we use, converts this number mathematically into the scale we use, and it gives us the pH of 1. Likewise, we could go over here and see something that has a pH of 3, and we could see that its H3O concentration, again with a little calculation, is 1 times 10 to the negative third molar. And what you can kind of see in terms of a pattern here is that the number that's the exponent ends up being the negative version of the number that actually ends up showing up on the pH scale. And that's basically what these logarithms are doing for us, is it's getting rid of all the rest of this junk and just focusing on the magnitude of the number, which has more to do with its power. Likewise, we can go all the way down here just for one more example. You can probably predict in advance the H3O ion concentration of something with a pH of 10. Now we're talking about a base is going to be 1 times 10 to the negative 10th molar. And what we can see here, by the way, it's kind of interesting, as we go down the scale in this direction, this is a much, much smaller number than the numbers we're dealing with over here. This is 0.1, this is 0.001, and this is 0.00 over and over again 1. This is a very, very tiny value, because in a base, the H3O concentration has dropped significantly because it's been canceled out by a lot of these OHs. And these OHs react, there's a neutralization reaction, and the end result is we expect to see very little hydronium ion, which is exactly what we're talking about here. Before we move on, and unfortunately to make this a little bit more complicated, there was also that pOH scale that we were talking about. And the important thing to remember about the pOH scale is that it is opposite to the pH scale. So when pH is very high, that means your pOH is going to be very low, and vice versa. Likewise, if you're talking about the pOH scale, we can have the opposite here. Low numbers equal a very high concentration of OH minus, whereas before it was the opposite, and high numbers on the scale equal a very low concentration of OH. Which means that things that are on the pOH scale are alkaline when they are the numbers 0 through 7, and things on the pOH scale are basic, or they're acidic when they're on the scale of 7 through 14. We're not going to do a lot with the pOH scale. It's not something we work with very frequently. More than anything, it's just something we can convert back and forth with. But generally speaking, this is the scale that is most commonly used by scientists to describe the strength of an acid or the strength of a base. Now, as I said earlier, there are a couple extra equations that we can use to very easily and conveniently convert back between these two factors, and these are the two equations we're dealing with right here. The first one over here says that if you take your pH, whatever it is, and you add it to your pOH, whatever it is, no matter what your solution is, those two guys have to add up to the total number of 14, which, if you recall, is the maximum scale of our pH scale. So that's a quick and easy conversion between the two of those. Likewise, if we take our acid concentration, our H3O plus, and multiply it with our OH minus concentration, we get the number 1 times 10 to the negative 14th. Again, no matter what solution you have, and no matter how you try these things. And if you really look at it, if you're starting to understand how this P scale works, you can recognize that these two equations say exactly the same thing. If we took the H3O plus concentration and the OH minus concentration and take the negative log of each of these, we would get pH and OH, and if we took the negative log of 1 times 10 to the negative 14th, we would get the number 14. So it's really just a conversion between the two. But again, if you're dealing with the pHs and the pOHs, this is a more convenient equation to use. If instead you have the concentrations of the ions, this is the more convenient equation to use. But in either case, both of them get you at the same result. Before we move on to some of the actual mathematics and practicing some problems here, I want to talk about the concept of actually measuring pH as opposed to calculating it. And there's a couple ways of doing this, two of which are very, very simple. The first way of measuring pH is a little on the cruder side, but if you're just looking for a general idea of where you stand, litmus paper is a tool that you can use. And if you've done any work with acids in your science classes before, a litmus paper is probably something that you've played around with. And we got a picture over there on the right. Basically, the way litmus paper works is it's a small piece of paper. It's infused with a chemical compound, and this chemical compound changes color based on the acid concentration. What you can see on the actual wheel, on the actual piece of the device for holding it, is that there's a color scale on it, and you can notice in very tiny numbers there that each number, each pH value, is associated with a different color. When you put your litmus paper in acid, it will change color accordingly. You then match that color up to one of the sheets there, or one of the colors on the scale, and you'll get a general idea with very few number of significant digits as to what the pH of your sample actually is. If you're looking to measure the pH of your sample a little bit more accurately and get a little bit more information, you can use a digital pH meter. And these come in lots of different fashions. This is actually a relatively large lab-based one, but you can also get very portable versions of this. This device is obviously a little bit more complicated. The probe on the end, which is the thing that's in our solution there, is made of a special type of gas, and it's filled with a solution that is at a constant pH. And actually, it's a very fragile piece of equipment that has to be stored very, very carefully. Basically, what happens then, it kind of really generalize a little bit, is that there are electrodes attached to this meter, and as a result of putting it in a solution with a different pH, it causes an electrical imbalance between the inside and the outside of the glass, and the device is able to read that electrical potential and display it as a number. The further you are from the solution that's in the inside, the larger the potential you get, and it translates into a larger or smaller number or pH value that's registered on the device itself. Either way you use, both of these are ways of getting pH data about the sample that you have, and then that pH data can then be put into the equations we have from before to give you more information about either the concentration of the ions or the opposite, the pOH value. Alright, so we've now taken some time. We really covered all the main ideas of dealing with the p-scale with pOH and pOH. It's time to take a minute now and do some of the calculations associated with these. I think it's actually a great idea right now. We haven't done one of these yet together, but the equations are simple enough that I think you can take a try with this just using your graphing calculators. Take a minute, pause the video, see if you can calculate the pH concentration of this solution. That'll be the easy one to calculate. And then, using some of those extra equations, see if you can't calculate the pOH of the solution. And there's actually a couple different ways you can attack this. Like I said, take a minute, try this on your own. We'll go over the answer together in a couple seconds. Now that you've had a chance to take a swing at this problem, let's start by calculating the pH of this particular solution. That pH is to be equal to the negative log of the H3O ion concentration, and I tell you the H3O ion concentration right here, which means our pH therefore is going to be equal to the negative log of 2.83 times 10 to the negative fifth. This is really just an exercise in using your calculator. You're going to type in this number into your calculator right here using scientific notation, and then simply press the log button. And when you do that, you're going to get an answer of this right here. We get 4.548, and that's actually going to be a negative 4.548 because it's a negative power that we start with over here. But notice in the formula it's the negative log, which means the negative signs cancel out between the number, and we end up getting the pH of 4.548 as the pH of our actual solution. Once we know this bit of information, we can then use this to calculate the pOH, because we know that the pH plus the pOH must ultimately equal the number of 14. Well, we already know the pOH, or the pH, is 4.548, and we know that the pOH is something we're looking for, and all of that has to add up to 14. When you plug those things into your calculator, we can then solve for our pOH as being equal to 9.452. 9.452 for our pOH value. And again, both of these numbers are measurements of the concentration, basically convenient measurements of the concentration of H3O ions from above. Here's a similar problem, but we're going to be working in the opposite direction. In this scenario, you're given the pH of your solution, and you're ultimately asked to go back and calculate what the H3O ion concentration and what the pOH ion concentration is. So again, we'll deal with our equation here. pH is equal to the negative log of the H3O ion concentration. But in this case, we know different information than we did before. Now we're going to plug in the number 9.13 is going to be equal to negative log of the H3O ion concentration. Now again, you might be a little bit rusty with some of your algebra here, but in terms of solving through this, we got to use the inverse function of the negative log, which, if you recall from algebra 2, is your 10 to the x function. And we're going to do that to both sides. So what I'm going to do in this scenario is I'm going to take this number, 9.13, and I'm going to plug that into my calculator. In fact, actually, let's do this first. We're going to move our negative sign first. We're going to get negative 9.13. I'm going to plug that into my calculator, and then I'm going to use the 10 to the x button. Very often, this is the button that is on top of your log button. So what we'll do then is we'll take this negative 9.13 and push that 10 to the x button, and we're going to get our equation that's going to look like this. That's going to cancel out the log on this side, and it's going to get a numerical value on that side, giving us that the H3O concentration in this case is going to be 7.41 times 10 to the negative 10th molar. And again, this 9.13 is a basic solution. In a basic solution, we would expect to see very little H3O, very little acid, and that's exactly what we see here. This 7.41 times 10 to the negative 10th is a very, very tiny number. Now again, the question also asks for what the pOH is going to be, and we can recall this equation in terms of our extra equations from before. The hydronium ion concentration times the hydroxide ion concentration has to add up to, multiply together to 1 times 10 to the negative 14th. Well, we know that this number here is 7.41 times 10 to the negative 10th. We can multiply that by our hydroxide concentration, and all of that has to equal to 1 times 10 to the negative 14th. If we want to solve for our hydroxide ion concentration, we can take our 1 times 10 to the negative 14th and divide that by the answer we got from before, and we end up getting the number 1.34. So we get concentration of our hydroxide ion is equal to 1.34 times 10 to the negative 5th, again, molar. Again, this concentration is much higher than our concentration of H3O+, but that's not such a big surprise. Again, 9.13 is a basic solution, which means it has a higher concentration of hydroxide ions, and it's exactly what our math here has told us. So we get our OH minus concentration over here, and we get our H3O concentration. Before we wrap things up for the day, we got 2 more problems I want to be taking a look at, and that's calculating the pH of solutions of acids. And this is something we're going to do on a very regular basis to get an idea of what it is we're dealing with. For example, we can calculate the pH of a 0.1 molar nitric acid, HNO3. If you recall back in the beginning of the video, we're not interested in plugging the concentration of the acid into our log equation. It's the concentration of the H3O+ that we get. And we actually have to see the reaction to figure this out. So we're going to write our HNO3. We're going to react that with our water. In this case, HNO3 is going to be our acid. It's our proton donor. And as a result, we're going to get the H3O+ ion, and we're going to get the NO3 minus ion as a result. Notice here that the balanced version of this reaction, that 1 mole of HNO3 gave us 1 mole of the hydronium ions. This means that our 0.1 molar NO3 solution is going to give us a 0.1 molar hydronium ion solution. And once we know that hydronium ion solution, we're ready to actually do the math and determine the pH of the solution. We know again that the pH is equal to the negative log of, in this case, the 0.1. As you start getting better with your logarithms, you can automatically see that the log of 0.1 is going to get us the answer of -1. That -1 is going to cancel everything out, and we'll find out that the pH of this solution is simply going to be the number 1. If you're not that comfortable with your logarithms, your calculator would have gotten you the exact same answer. To finally drive this last point home, we're going to do the same exact calculation, but this time with a different acid. Instead of using nitric acid, which was monoprotic, we're going to use sulfuric acid, which is the example we had from before, as our diprotic acid. Again, we got to look at the reaction. H2SO4 is going to react with the water in our solution, and it's going to create our hydronium ions. The H's here are going to get donated to the water, meaning H2SO4 is our acid, our Bronsted-Lowry acid, and water is our Bronsted-Lowry base. And that's going to be combined then with the sulfate ion, which is a charge of -2. The thing that makes this problem different is that when we balance, we get 2 hydronium ions for every 1 sulfuric acid we start with. That means that our 0.1 molar H2SO4 solution really has a hydronium ion concentration of 0.2 molar. Because we get twice as many hydronium ions for every one of these guys, we get twice the concentration of hydronium that we did of H2SO4. Again, once we've identified this value, it's simply a matter of plugging it into our pH equation. The pH of this solution is equal to the negative log of the number 0.2. And as good as I was with the last problem of being able to do this one in my head, I certainly can't do this one that way. So we'll take a second with our calculators. We'll take 0.2 in the log. We'll take the negative sign of that, and we'll find out our pH in this case is negative 0.699 for our pH. Notice that the pH of this one is lower than the pH of the nitric acid, and that makes perfect sense. By changing the pH, that's suggesting that the hydronium ion concentration is getting bigger, and that's exactly what we said was happening in this problem. Because it's a diprotic acid, we got a higher concentration of hydronium ions. This accounts for pretty much all the calculations I'm going to hold you responsible for in terms of acids. We'll take some time obviously in class to practice these a little bit more and also to clarify some of these ideas. Overall, I find the concept is relatively simple. If it weren't for those logs thing, we'd be going through this super duper quick. But the logs do definitely throw people for a bit of a loop, so we'll take some time to make sure that we work on that.